Hopefully you got the memo and are not just revising definitions ahead of your chemistry exams. The enthalpy topic across modules 3 and 5 on the OCR specification is a great example of why, because each and every one of these definitions has an associated reaction equation, which is much more likely to come up than the actual definitions themselves. Two of these are actually not even in the specification with a discrete definition, and the instruction is just to learn the reaction equation instead. Clearly, there's a lot to unpick here, but don't worry, because in this tutorial, I'll be giving you a full rundown of all the information and dropping in some exam and revision tips along the way. We are starting out here with lattice enthalpy, which is defined in the OCR specification as the enthalpy change for the formation of 1 mole of ionic lattice from gaseous ions. The 1 mole here is really important, and it's reflected in the structure for the associated reaction equation. When you write the reaction equation, you must make sure you only make 1 mole of this ionic lattice product. No multiples are allowed here whatsoever of these equations if they are to match the definition. Furthermore, the left-hand side must also be balanced correctly to reflect this. The other thing here, which will be a running theme, to be honest, through all these definitions, is the attention to detail we need to have when it comes to the state symbols. Here, they need to be gaseous ions on the left, and then the solid ionic lattice on the right. Moving on, and we have enthalpy of combustion. This is actually a year 1 definition and doesn't really come up very often in the second year, but it is defined as the enthalpy change for the complete combustion of 1 mole of a substance. Here you are most likely going to be given the standard condition state symbol for the substance you are combusting, as we're not super familiar with loads of different things under standard conditions, especially if we look at organic structures. And then all the others need to be standard conditions as well, but we are familiar with things like CO2 and water, what with us all being alive. The balancing again needs to be very specific. The substance being combusted must only be 1 mole in the balanced reaction equation, and then everything else needs to be balanced in respect to that. That means what's very likely to happen in a great deal of examples is you're going to need to use a half coefficient in front of the oxygen in these combustion reaction equations. So you do need to get used to using either 7.5 or 7.5, like I have done here for this one, which is for benzene. Once again, no multiples at all, in case I've not emphasized this enough here. You can't have just a multiple of this equation and expect that value to represent the standard enthalpy of combustion. Next up, we have enthalpy of neutralization. Doesn't come up very often, but here's the definition. It's the enthalpy change for the formation of 1 mole of water by neutralization. This one, like I said, isn't really on the spec very much. It only really comes up in first year in a very small instance, but it being rather simple just means that you might overlook it. Keep an eye on that 1 mole of water part. It is really impossible to balance every neutralization reaction equation to create just 1 mole of water, so you may need to adjust some data when this does come up in exam questions. For instance, if there was a situation where 2 H2O were being created and you couldn't balance this any other way, you would need to divide the reaction enthalpy change by 2 to get a per mole of water value, which then would be the enthalpy of neutralization for that reaction. Next up, we have what, if I had a personal favourite, it would be this one, but it is probably just the most popular. The one that's most common in the whole list, as it comes up heavily in both Year 1 and Year 2 exam questions, is enthalpy of formation. And it's defined in the OCR specification as the enthalpy change for the formation of 1 mole of a compound from its elements. This one needs extra careful focus on the state symbols. I know we've emphasised that already so far, but here it is really important. Especially if the halogens are involved. You need to know that the standard condition states for fluorine, chlorine, bromine and iodine are gas, liquid and solid respectively. These are such common exam mistakes. Please watch out for these. And also watch out for your handwriting, because they've picked up that when people rush, a S solid state symbol starts to look like a G gas state symbol. So please do be really careful with that. Again, like before, you need to make sure that you balance to create only 1 mole of product. So you've got to make just 1 mole of the product here. And again, much like the enthalpy of combustion, you're going to need to get used to potentially using the half coefficients here. You could use 0.5 instead of a half, but try and avoid any improper fractions where suitable. Moving on to enthalpy of atomization, and whilst this is defined as the enthalpy change for the formation of 1 mole of gaseous atoms from the element under standard conditions, currently on the OCR spec, this definition is not required, just the reaction equation is. However, that doesn't mean they couldn't ask you to explain the term in the exam and have a more flexible mark scheme to allow people not to kick off about the fact that their definition is not stated in the spec. My advice is to learn it and the equation regardless. It's not a great deal extra, and to be honest, the phrasing that's in the definition will help you understand the structure of the all-important reaction equations. I've given you a metal and a non-metal example here, and the products must be strictly 1 mole of gaseous atoms. So especially this one for bromine here, what you're not allowed to do is just ignore the half coefficient and make 2 Br gas instead. It must be 1 mole of the product with all the other balancing reflecting this. When you have a metal in these, like this calcium one, really, honestly, it's just a state symbol change. But you just got to be extra careful with that and don't have that little voice at the back of your head in the exam that says, you've missed something out here for this one. It literally is just that state symbol change when it comes to a metal. Our next enthalpy change here is not really first introduced to you as an enthalpy change, despite it having units of kilojoules per mole, because it comes up when you are studying periodicity in the first year of your course. This is first ionization energy, and it's defined as the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. I have noticed that the AQA definition is actually slightly stricter of this, and it does usually require you to say that it's the minimum amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. Like all the other definitions, though, that 1 mole bit is absolutely mandatory, so do watch out for that. The first equation is for the first ionization energy here of manganese, and you'll notice here we go from 1 mole of gaseous atoms to 1 mole of gaseous ions, and then we've got the electron over here. According to a lot of examiners' reports, a common error here is to put the electron on the wrong side. Not quite sure I agree about that. I don't remember seeing that myself too often, but watch out all the same. If they're saying it is, then maybe it's more of a national thing that I'm aware of. Be mindful that successive ionization energies that you don't need to be able to define will always start, though, in their reaction equations from the previous step's gaseous ion. So, for example, I've included here the third ionization energy of chlorine, and notice that it started from an already 2+ cation, and then it goes to the 3+ and the single electron. Remember, with ionization energies, it's one at a time, not all at once. That's why it's called successive ionization energies. Closely associated to ionization energy, we have electron affinity. Remember, they are both present on a Born-Haber cycle. I actually hate this definition, and thankfully, much like atomization, it's not currently one listed as a must-know in the specification for OCR. Now, despite this, I would still recommend learning a general format for the phrasing. It does help you learn the reaction equation, and you absolutely must learn that. It's defined as follows. The enthalpy change for when 1 electron is added to each atom in 1 mole of gaseous atoms to form 1 mole of gaseous 1- ions. See, it just rolls off the tongue, doesn't it? It's awful. I can't stand it. But the reaction equation is phenomenally important because we know that first electron affinity, for example, is a mandatory part of all the different Born-Haber cycles that we meet for those lattice structures in the second year of the course. So please make sure that you've got this first electron affinity reaction equation completely sussed. Second electron affinity, just here, is taking it one step further, and it's creating a 2- ion from an already singly negative ion. The first and second electron affinities for oxygen are actually exothermic and endothermic, respectively. That's right, they have different signs for these respective enthalpy changes. For more information on this, check out the video linked on screen now at the very top, or via the link in the video description at the end. A very short but sweet one up next, which is for enthalpy of solution. The specification defines this very succinctly as the enthalpy change for dissolving 1 mole of solute. Notice that the reaction equation we have here actually uses an aqueous instead of an H2O to represent the water that's being added here to the solute. Otherwise, if we used H2O, we would have to account for all the hydrogens and oxygens in the balancing. The balancing here must be strictly 1 mole of the solute, so look at these extra labels just here, and the products need to be balanced to reflect this. You also need to make sure that you don't go too far and split up the ions, which should actually remain intact. For example here, I've used and written the equation which has carbonate in here. So I've gone for potassium carbonate as my solute, and we know our group 1 metal carbonates are very soluble. And over here, I've created this CO3 2- aqueous ion. Do not go overboard and start breaking up the carbonate ion. Much like ions of sulfate, ammonium, which is of course positive, hydroxide, etc., these all need to stay intact. Refer to your common ions and formulae list for more guidance, which you can currently find in Module 2 of the OCR specification. And I'll drop a link at the bottom in the video description to help with that. Last of all, but by no means least, it's enthalpy of hydration. Much like lattice enthalpy, you actually need to know some trend data for enthalpy of hydration, and there's a link on screen now that'll take you straight to that video once you finish this one. Enthalpy of hydration looks pretty similar, and actually sounds pretty similar in the definition, as enthalpy of solution. So make sure you take the time to distinguish between these two. I would pair them together on flashcards, so you could maybe test yourself on 3 different reaction equations from all these different enthalpy changes on a single card, and I would put these both on there to make sure you are drawing your attention to both the similarities and the differences between enthalpy of hydration and enthalpy of solution. The specification currently defines enthalpy of hydration as the enthalpy change for dissolving 1 mole of gaseous ions in water. The reaction equation here is essentially a glorified state symbol change, and it's another use of the aqueous state symbol in the reaction equation instead of using H2O. As I've already mentioned, we don't want to introduce a load of extra hydrogens and oxygens, which messes about with the balancing, when all we're trying to do is get something to dissolve in water. For this reaction equation, we are simply going, when we look at our ions, from gaseous ions to aqueous ions. And it's only 1 ion at a time with this. So that might need to be reflected in your calculations should you have 2 in a lattice formula. Thanks so much for watching this tutorial. Next up, you're going to need to understand which of these reaction equations are exothermic and endothermic. So I do recommend that you follow the links on screen now. And you could also see all of these enthalpy changes in action, well, most of them anyway, in a Born-Haber cycle. So click the link on screen now to be taken to that as well. Until next time though, everybody, happy revising.